Welcome, learners. Today I will talk about community detection in complex networks, trends and issues. This session is intended for the learners who are actually pursuing PhD program in mathematics, especially in the field of complex networks and network science. So in this session, I am going to talk about what are the current issues that challenge the community detection researchers, especially, and what are the methods available, what are the quality metrics, and how we tackle those problems. I will just start with a brief overview of what are complex networks and what are their fundamental characteristics. So in this direction, I would just point you towards three major research articles which not only just saved the network science, they actually shook the whole area of network science and complex networks, or the study of community detection algorithms. These papers were published by three eminent scientists. So I will just look at those papers. The first one is by Watts and Stroges. It just talks about collective dynamics of small world networks. It was published in the journal Nature in 1998. Second one is by Barabasi and Albert. It talks about the emergence of scaling in random networks. And the third one is by Rawaz et al. So there are actually 5 authors, and it just talks about hierarchical organization of modularity in metabolic networks. So these are 3 research articles, but fourth one it just talks about what are the current methods, like what are the structure and function of complex networks. Just reviews all the methods available in the field of complex networks. So let me just go into more detail about these 3 major articles. Like if you look at the Watts and Stroges paper, so they actually started from regular lattice, and then they give a model of random networks where a very tiny fraction of edges are removed and they are then rewired randomly. So you may know that a regular lattice is just a regular graph of a fixed dimension. For example, the figure shown on the leftmost side here is a regular graph of dimension 1. It is actually 4 regular. So such a graph is actually highly clustered. You can see that every node has clustering coefficient 1. So it is highly clustered, but its average shortest path length is actually quite high. In other words, it means that it is dependent. It is of the order of linear in terms of the number of nodes. So when you look at this network, now just remove any pair of adjacent edges and just rewire them randomly. What you get is a network of this kind where the clustering coefficient is still the same. There is no much change in the clustering coefficient, but there is a huge decrease in the average shortest path length, which is called also the characteristic path length. So now this property is actually that they found in real in complex network. They actually described it, and they found that this is present in many real world networks that emerge from real domains like computer science, social sciences, technology, medicine, or from many humanities or any other kind of like biological networks. And they have observed that all those networks have very small characteristic path length, and yet they have high clustering coefficient. So this was the one of the fundamental characteristics of real world networks. And then the second one is by Barabasi and Albert. So the Barabasi and Albert actually they discovered how real world networks organize themselves. So there is something called preferential attachment strategy, and it just talks about, say, when a new node joins to an existing group of nodes. So what is the criteria, or on which basis it just joins that group? So when a new node joins, it actually looks for the node which is highly connected, that is, which has high degree. In sociological context, you can say that the person which are already popular, they become even more popular over time. So this kind of phenomenon was just observed in real world networks as well. And to just study this in a systematic way, Baravasi and Albert actually computed the degree distributions of the different kind of real world networks, and what they found was that the degree distribution follow the power law, and which is this: Pk is directly proportional to K inverse gamma, where gamma they have observed for most of the time it was lying between 2 and 3. So now, okay, now what is Pk? Pk is actually the probability of a node having degree k. Okay, so the probability of having probability of a node occurring with probability k is directly proportional to k inverse gamma. This means that when k is high, Pk is less, small, right? So the nodes of high degree occur in less number, whereas the nodes of low degree occur in abundance. So this kind of property was seen in almost all the real world networks they have studied in the article. So this property they have also called scale free property. Why scale free? Because no matter at what scale you look at the network, that means you pick up any small portion of the network, you will find that that portion also possesses the same property. So in that way the network is scale free. Okay, and then the third characteristic was discovered by Ravaz et al. In 2002. So the key contributions of Ravaz was this: they actually have, in the previous researchers have discovered that real world networks have a scale free property and high clustering coefficient. Okay, so Ravaz et al. Thought that what could be the reason behind these two properties which occur simultaneously. So they actually constructed a model of real world networks where they had hierarchical characteristics. Now hierarchical characteristics means they constructed a small group of nodes where there was one node of high degree and remaining nodes for having low degree, and then they just replicated it and just put one central node and keep on growing it in this way, so that the whole network, when you look at from the top, you will find that there will be very few nodes of high degree, and but having very large number of nodes of small degree. So that that model actually mimics the scale free characteristic of networks. And then they studied that the clustering coefficient of those networks actually also follows the power law, and it is this power law: Ck is directly proportional to K inverse beta, where beta is roughly equal to 1. Ck is the clustering coefficient of a node with degree k. Okay, so now Ck is directly proportional to K inverse beta. It means that the nodes of high degree have low clustering coefficient. On the other hand, the nodes of low degree have large clustering coefficient. So, and then they have also discovered that the modularity is hierarchically organized, and so these were the three fundamental articles where you can see that three fundamental characteristics of networks were discovered: the small world property, scale free property, and the hierarchical organization. So then comes the next thing: the hierarchically organized network is actually organized into a smaller number of modules. So if you just look at the top level, you will find that this network is composed of very few modules, but those modules are further divided into sub-modules and so on. So this is what is called hierarchical organization of network. And then there was some review article written by Newman in 2003 that reviewed all the existing methods of that were used by researchers for studying complex networks, and they have just discovered that they are the properties: scale-free, small world transitivity, or high clustering coefficient. And they also discovered, gave some mathematical models of networks, like what are the Eidos-Renyi model, Watts-Stroh-Gauge model, or Barabasi-Albert model. Okay, and then there was an article by Newman and Girvan, and this was the article which could be thought of as the first article where they not only talked about modularity, they actually gave a criteria to measure the modularity of networks. So there was actually, thus far we have seen that the modularity was a characteristic of real world networks. That means the real world networks are organized into different modules. But Newman and Girvan actually gone further. They devised an algorithm to detect communities or modules, and then they also devised a quality measure which they also named as modularity. So this measure could just compute how strong the detected community structure was, and it just measure varies from -1 to 1. So where 1 means that the community structure or the modular structure is very strong, whereas -1 indicates that structure is very weak, or in other words, it can be seen as say anti-community structure. Whereas a modularity of 0 means that the network has neither a community or an anti-community structure. It is just like a random network. So, and then there is a very interesting article by Blondel et al. So this article actually was, there is some story about this article. This was first archived on March 4, 2008. This article was actually based on the master's thesis of one of his authors called Lefebvre, and there was some very unfortunate situation with this article. It was rejected from Nature as well as from PNAS, Proceedings of National Academy of Sciences. And then they maybe after frustration, they actually submitted this article to the Journal of Statistical Mechanics, Theory and Experiment, and there this article was published in the same year. Okay, so the story now starts from there. The same 4 authors, they after 15 years, they just revised their article, and what they have seen that their article crossed 20,000 citations. So they came up with a new article with the same name. Actually, only 3 of the authors came with the new article, The Fast Unfolding of Communities in Large Networks, 15 years later. And now, so by this time, this article has already crossed 26,000 citations. Okay, now, so what was the content of this article? What was there? Why it was being cited too many times? So they analyzed this article, and what they found that this article has been cited in various kind of journals. For example, it has been cited 428 times in the journal Lecture Notes in Computer Science, 263 times in PLOS 1, and likewise you can see that these are the citations of this article in different journals, and these journals are Scientific Reports, Physica A, IEEE Access, Physical Review E, Nature Communications, and Information Sciences, PNAS as well. So these were the things that actually, so there was something very important that was given in this article, and that was actually an algorithm that could detect community structure in large networks in very small number of time, very fast. So we shall come to this algorithm shortly. So first let me just describe what is community structure and how it can be useful to the wide audience. So there are some things that we have seen, like real world networks are sparse, scale free, modular, and hierarchically organized. So what is community structure? So if you just look at a social network, then in a social network, community structure could be something like a group of persons with similar traits or habits. On the other hand, if you look at a gene co-expression network, then in such a network, the community structure could be a functionally related genes. And whereas, say, if you look at the internet, then a community on that network is actually a group of web pages on the same topic or similar topic. Likewise, so there are many ways which you can define community structure, and in fact, due to the vagueness of the community structure concept, we came out in 2021 with a formal approach to community detection. This was our article, Formalizing and Detecting Community Structure in Real World Complex Networks. It was published in Journal of System Science and Complexity. So we actually talked about many things there, like we introduced what we mean by peak communities or local maximal peak communities, what are hubs and what are outliers. And not only this, we also talked about, we also introduced actually some innovative method to detect communities, hubs and outliers. So this is just one, as in this graph you can see that this is just a model community structure. Broadly you can see that this is divided into 4 groups, 4 modules, 4 communities. But if you look at each community, then you will see that this community is itself divided into sub communities. And apart from this, some communities have overlapping nodes. So this is how, when you look at a network from just from broadly, you will see that it is divided into different kind of modules or different kind of communities. Now, why it is needed to study community structure? There are many reasons. First thing is that when you look at a network, there are 2 ways. Either you can look at the individual nodes level, that is at the bottom level. There you can study the individual nodes degrees, degree distributions, strengths in case the network is weighted. Or you can also look at the network from the top level, and there you can study how many nodes are there, how many edges are there, what is the clustering coefficient, and so on, what is the diameter. But these things actually do not tell anything about what is hidden in the network or how the network is organized at intermediate level. So do you want to understand the structure of the network at intermediate level, then you need to know the concept of community structure, and then you need to also know what are the algorithms or methods available for community structure. Of course, this is one reason. There are many other, like community structure can explain what are the processes or how the processes spread on networks. For example, how infectious diseases is spread through networks. This has been well studied using the concept community structure. Or if you want to see how different, like nowadays you can see that when you open your social media accounts like Facebook, you will see that every day you will find that, okay, you may know this person, you may know this person. So how do you know, how such recommendations are coming? You don't even know that there are algorithms. These e-commerce or these social platforms are actually using very smart algorithms to just gather information about your friendship, your network, your habits, and then using those information, they actually recommend things to you. For example, when you purchase some product from an e-commerce site, you will see that it also recommends something like, okay, if you have purchased this item, you can also purchase this one. So why this kind of things is happening? Because these are these kind of companies actually use community traction algorithms at a large scale. So they study the habits of customers, what kind of product say one purchases, and then what kind of other products also being purchased by the same person simultaneously. So those habits are then recorded, analyzed, and then those things are based on those recordings, or they are recommended. So there are many applications. Of course, it can also be used in predicting future scientific disciplines. What will be what are the current hot topics on in a particular field? You can very well analyze this using the concept of community structure. Okay, so now I just come to what is the algorithm that was discovered by Blondel et al. So this algorithm is known as Lowen algorithm. The idea is simple. I can explain it to you using the graphical. Say this is a network. So initially what happens, each node in the network is labeled differently. That means with a different color. And then at the next iteration, what happens, each node is just checked for its community. That is, it's checked for its neighboring community, and if it is say shifted to its neighboring community, and then the modularity of that shifting is computed. That means if it is removed from its original community and shifted to the neighboring community, and then gain in the modularity is computed, and this is done for each of its neighboring communities, and the community for which the gain is highest, that is picked. So in that case, that node goes to the most appropriate community, and this happens for each and every node. Okay, so there after one iteration, you will see that some community or some labels have already disappeared and only few labels remain, and then using those labels a new network is constructed, and again the same technique is applied on this network. And so this iteration keeps on going as long as there is an improvement in the modularity. So this way you will see that after some finite number of iterations, the algorithm will stop and you will get the community structure. So this can be seen in 3 steps here. This is the initial condition where you will see that each node has distinct communities. This is the intermediate level where some labels have disappeared, and then it is the final situation where there are only 2 communities. So the idea of Lowen was very fascinating, very simple, but there were some issues with this algorithm, like it could not handle it has the resolution limit problem. And what is this? Resolution limit just tells that any algorithm that possesses the resolution limit cannot detect communities smaller than a particular size. So this was one problem, and not only this was the problem with this Lowen. In fact, many algorithms that optimize modularity or any other kind of objective function, they also suffer with this kind of resolution limit. Apart from this, Lowen also has problem with like detecting badly connected communities or disconnected communities. And then there were certainly some improvements, like some new algorithms have been developed which were fast greedy, LEDEN, LCOM and PDFS. I would just point you to that. Now what are the challenges that are being faced in this area? I just come to the current challenges. So we have talked about there are algorithms that can detect communities, which can detect community very fast also, but there are issues with those algorithms, like they have their quality is not of that high nature. So we need to develop first very fast algorithms. We also need to develop quality measures which are better in terms of assessing algorithms. And there are also lack of artificial benchmark graphs. Like there are some graphs like LFR or Newman-Grivan or ABCD, but these are not sufficient. We need more kind of some graphs. And then of course algorithms for node or edge attributed networks are missing. There are very few. We need to discuss them. So these are the some current issues that are available in this field, and this field is very highly growing. So thank you all.